on just a minute.
Okay, you're good.
Okay. Okay. So let's continue on to the first step. So for this part of the talk, we're going to be discussing geometry and setting up Laplace's equation in MOOS. And so first, what's our problem? So we've got the standard Laplace's equation. And to do that, in MOOS, we don't need to solve any code. So you might remember the weak form discussion I was talking about earlier, taking your strong form of your equation, the form that's written down on paper, and converting it into something that's more amenable to finite elements. So that Laplace's equation will have a weak form shown at the top. So this is in inner product notation. So you have your integral of the gradient of v times the gradient of your basis function, minus your boundary condition term there equals 0. So for right now, we're just going to ignore the boundary condition term, and we'll just set that term equal to 0. And the structure of this is similar to what we need for Poisson's equation. So and then in MOOS, this is called a diffusion object, as part of its history in neutronics and those sort of particle fluid calculations. So this is it already exists in MOOS, so we don't need to add any new code to do this. All we need to do is specify the geometry and set up a 1D Cartesian problem, define the boundary conditions that we want to pose on those boundaries, and then we can do all of that inside the input file for this step without making anything new. So this is a chunk of a MOOS input file. And so if you want to look at this on your computer, it's in the tutorial application under step 1. So first of all, we're generating a mesh. So this top block right here, any chunk of code in the MOOS input file, it has a type. So in this case, we're creating our mesh. So we have our mesh block with type of generated mesh. So we can generate lines, rectangles, and boxes with this. We wanted to do a 1D example, so we're saying the dimension for that mesh is going to be 1. Nx is the number of elements, so we're saying we'll give it 100 elements. And we have a maximum value in the x direction of 2.54. So x-min, y-min, z-min, those are all 0. But y-min and z-min don't matter because they're overridden by the dimension equals 1. So if we want to do a square, or a line in this case, a 1D domain, with a maximum of 2.54, that's all we need to do. We don't need to say x-min equals 0, it's already there. So moving on to the next block, we want to set up our variables. So that's because by default, the MOOS applies a linear Lagrange basis function. So a basis function, and we'll go into this more in a minute, but a basis function that is 1 at the node that you're interested in, and 0 at all the neighboring nodes, and linear in between. So naming your variable and leaving it blank here, that's the default. And you'll have an order and a family associated with it if you want to change it from there. And you label that just like you would this. So say you want a second. So now we have our kernels block. So kernels they're your pieces of physics in your simulation. So in this case, because we have a very simple equation, we can use built-in code. So we can use the diffusion kernel that already exists in MOOS, and from this, sure.
What about the physical units? 2.54 centimeters.
Right. So the units. So the calculations before you set it in units, the calculations are done unitless. So you as the developer need to define what units you're using. So if you're sticking with meters and if you're working in a system where you have to do a lot of unit conversion, sometimes it may be easier to, and this is done in Zapdos, where you have your base unit system, but then you're inputting things with their native units and scaling them as you need to in order to be consistent. So you can do that on a code level. You can do that on an input file level by changing, like you can set up a global parameter for your units and set them. So it's really kind of ad hoc, however you want or need to do it for your problem. Okay, so now we've defined our mesh, we've defined the variables that we're solving for, and we've defined our physics, or their physics term, or our actual term in our equation. But we still need to define our boundary conditions. So in this case, it simply means the variable that's being operated on. So your u equals some value. So a variable, again, is our potential. On the left boundary, we're saying we're giving it a value of 100, or 100 volts. So on the right, we have another Dirichlet BC with a variable operating on potential on the right boundary. So for Moose, to denote your side, which is, I think default is 0 and 1 for a 1D mesh, and then it changes based on whether you're doing 2D or 3D. Or they're also readable and just saying left or right. Moose, the framework will understand what you're talking about. If you're creating your own mesh using an external software and bringing it in, you need to know either the number associated with the side set in the mesh, or Does anybody have any questions about any of that before I move on? This is the solver and executioner settings and that sort of thing, but does anybody have any questions before I get to this about how we've set up the equation so far? Okay. So this block here, these are default settings. This is setting up the type of problem they're using. So this is the normal type of finite element problem in Moose, FE problem. Most of the time you will never, this block here is mostly just for explanation purposes. For this, you don't even need to have this block because everything in there is default. So for executioner, we don't have any time derivatives or anything like that. It's a steady state problem, so we're setting type equals steady. We're using a solve type of preconditioned Jacobian-free Newton-Krylov, which we can go into that in a few slides. Then, because PET-C is the back end of Moose, or one of the pieces of the back end of Moose, we can have access to command line options, is Boomer AMG. So Boomer AMG is for like elliptic style problems, and that's what we have here. So just set those to be that setting, but you can change those. These are the command line options that you would put into PET-C if you were running something with PET-C. And so any questions about that, I would direct you to the PET-C user's guide. But you separate it up by iname, which is the actual what you're changing. You have an option that doesn't require an answer. You want to tell PET-C to do something specific, and it's just a flag. You also have access to that. And then, of course, we want to have our outputs block. We want to see the data that we're making. So we're telling it to output to an Exodus file format output file. You can output to various different output formats. What I generally tend to use is either Exodus or CSV, depending on the data. Okay. So before we move on any further, I wanted to ask all of you. And everything seems to be working okay? Okay. We've had some random. Okay. Well,
This is your copying from the GitHub tutorial stuff?
Yeah, the URL I showed earlier for GitHub, yeah?
So I downloaded it, but I haven't tried where I didn't do the install.
Okay, well, if you, after you have Moose installed and working, all you have to do is do make. I was going to let people get to that before we moved on much further. So, all right, I guess Corey's coming to help you out. Thanks, Corey. So after we've made this input file, and presumably at this point we've run it, and it looks good, we want to make a test because we want to make sure. Now in this case, it's not so important. This test actually comes with every problem, but uses a smaller mesh to increase the speed for a small problem like this. That's negligible, but in general, you will design a test surrounding a piece of physics that you've created, and then you'll make a test for it. And the structure of a Moose application is such that it's really easy to make a test. You'll see those Moose examples of that in the Moose/test/tests directory, where they're organized by the type of test they are, like whether it's testing a kernel, an auxiliary kernel, that sort of thing. In an application, you can load everything in that directory. You don't have to be as strict as Moose is about the directory labeling there. But you'll notice in the directory of the tutorial repository that your test directory has several things in it. You'll have a tests file, and that's where this block comes from. And it's structured in the same way as an input file in terms of you have a block, you have an interior level that has a name, and then some information about that interior block. So in this case, and for a good output file, a file that we know to be correct, of Laplace_out.e. And so this file would be located in a folder called gold in that directory. Moose knows that your good results are in the gold directory. And so when you do a test, when you run your tests, it'll take this input file, it'll run it, it'll output the data file from that run and compare it against what you made previously that you know to be. Again, this is the same input file that we saw before. The only difference is I've just decreased the number of elements to 20 instead of 100. Again, for a small test, the timing it takes is negligible, but for larger tests, it can make a difference. And all you're doing is testing the functionality. Okay. Did you have a question, Steve? Okay. So again, this is the same input file as before. I just put it up here as reference. And if you want to see this input file, you can see it in a tutorial. Before I move on we're going to go into some finite element principles. And I wanted to poll the room. How many of you are familiar with the finite element method? And how many let's start with how many are familiar with the finite element method? Okay, so a portion of the room. So how many are not at all familiar? Okay, so we got some extremes. So we'll go through some of this. This will take a little bit of time, I imagine. So feel free to stop me if it's structured. Sure.
Now that you've shown step 1 to running that on the screen,
Sure.
showing it compiled.
Yeah.
Kind of showed a lot of code. Kind of so much.
Sure.
Like on there.
Yeah. Well, okay. So okay. Since part of the room doesn't have it working, part of the room does. I'll get a working example of this up on the screen and run it and show everybody. So I think that'll be beneficial. So let me get that going. Okay.
You can center it. Remember, I got the ends of your screen chopped off.
Oh, do you?
Yeah, so full screen will be. There you go. You're good right there.
Okay. Well, I'll need to make it bigger though, so everybody can see it.
Command plus.
So to run this, I'm going to go to my projects directory and then tutorial.
This is something they could follow along on their computer, right?
Yeah. So if you set up Moose using the installation, the getting started instructions, it'll instruct you to make a projects directory to place Moose in. Feel free to place Moose. I think you can probably place it wherever you want, right? Or is it dictated, David, by the location? Okay. So. Okay. So for those of you who didn't hear, so if you're installing Moose and you're putting your application, we prefer it to be in the same directory. Moose and your application be in the same root directory. If not, then you have to specify where Moose is located, so your directory can find it. And so we'll go to that. And so here's a standard look at what a basic application looks like. And so we want to look for that test. So I already have it loaded up in tests. We're going to go to test, and then tests. And so we have all our tests here. So in this case, I'm going to go to step 1. And so, like I told you before, there's that structure of your test directory. So you have a gold directory. That's where your good result, then your test file. And so if we look at that, like you saw, that's what a test file generally looks like, just that one block. And then if I want to run this, then I need to go back or direct, go back to the file, the executable for your application that I've made. But actually, let's take a step and make it. Then you just need to type make, and then the number of J and the number of threads or the number of cores that you want to run. It'll make it. So after it makes it, it'll have your, so the default, when you type make and J8 or J, however many cores you have, the default is going to be an OPT executable. So that's an optimized executable. There are different versions of that. So if I want, then I would type method equals debug and then make J8. And that would rebuild my application in a less optimized mode so that if you needed to run it through a debugger, so if you're having an issue and there's like a memory problem or something like that that you can't track down in a simple way, you would want to make a debug version of this executable so you can run it with your debugger. Okay, so does anybody have any questions about any of that before I go back to, we're gonna run the input and follow along with me.
So if you got Moose running, this is a good chance to make sure that you feel good about everything and make sure it's running well on your computer.
So we're going back to our directory, our test directory. And so I'm going to run my compiled application, tutorial-opt. So you have your executable. In order to run an input file, step 1.i, I believe. Okay. So that would be the command I would use to run it. And so let's run it. And so if we look at output, a standard output for Moose, it'll give you some framework information, what commit you're on, what was the day that commit was made, to give you an idea of. Moose doesn't have standardized versions. It updates very, very frequently. So the version you're using, we use. So whenever you have an issue and you're posting to the Moose users group, very often you'll get questions about, well, what version of PETC do you have? What version of libmesh do you have? And those questions you can answer with this output. And you can also, if you can save this to a file automatically as well, if you essentially pipe the output out. But anyway, so it'll show you some information about your run. So in this case, I've just run a default command, and then if I've made any subdomains or partitions, then it'll give that information as well. It'll also give me my number of degrees of freedom, the variables that I have turned on or put in my input file, and then the finite element type and the finite element order for that type. It'll also give me executioner information, so steady versus transient, or even eigenvalue if you're setting up an eigenvalue problem. So then it'll go into the solve. So this is when you're putting in finite elements, when you're putting your strong form of your equation into a weak form. It's also called a residual form. So in the case of the example equation, you only have one term, so there's nothing to really move around. But so say you have, and what Moose is trying to do is to make the left-hand side of the equation get as close to 0 as possible. And so to minimize the residual. And so what you're seeing on your screen is every nonlinear step, and then every linear step inside of every nonlinear step. Now Moose makes some assumptions about based on your solver settings, what you're doing, in that if you have a default way of looking at your problem. But so as we can see, it minimized to a pretty good residual. And so that seems like it's a good run. Okay, so I will get to that in some other slides, but there are absolute and relative tolerances for your nonlinear steps and your linear steps, and those can be set in the input file. Maybe 6? Okay. And then it changes based on, I'm not familiar with all of the defaults off the top of my head. But you can change those in your executioner block as you need to, and those are all available to you. Go ahead.
Is there a fixed data type for the real numbers? Right. Or is there something that you can choose?
So Does that get your question answered? Okay. Okay. All right. So say I want to look at this data now that I made it. So in my, that's the solve. So it's there's a solve. Okay. So in my case, I'm using ParaView as my visualization software of choice. So if I want to look at this file, I'm going to have to open ParaView. And it didn't open on that screen, which is annoying. Okay. So this is ParaView, are not that hard to learn. So we'll not go too far into how to use ParaView, but so we're just going to open up that file we made. Dual screens, man. Just a second.
Oh, you got two screens on?
Yeah. Well, because I've got some stuff I'm looking up on here and throwing it up there. Step 1.out or underscore out.e. And okay. So back here. So we want to look at a plot of that data. So we go to render view. We go to sample data points along the line. Get rid of that. So let's find our variable here, potential. We'll select that so we can see it. And we'll plot it over a line. So this, you'll see in this the initial condition. So even if you are running a steady state solve, Moose will give you an initial condition. You can set an initial condition even for a steady state solve. So if you're trying to step through a problem up to a steady state in a traditional sense. So you'll see that 0 here because there is a default initial condition of 0. But if you play that, you'll go up to the 1 step, which is the only step you have, and you'll see our left boundary condition is 100, our left condition is 100, our right one is 0, and we're linear in between, which is what we expect. So if anybody has any trouble doing the same thing, say it again. This right here? Yeah. So yeah, plot overline is the name of it. Yeah. And so some of these the commonly used options are sitting here. You could do a lot of. Okay. So let's get back to the slides. So before I move on to a discussion of finite element principles as it relates to Moose, does anybody have any questions? Okay. So to introduce the idea of finding coefficients to a function, which is interpolating a set of points and trying to turn it into a function. You're looking for coefficients to a function that has that form. So where a, b, and c are your coefficients, and your 1, x, and x squared are the basis functions of your interpolated function. So we want to, in this case, we want to find a, b, and c, where ci are the coefficients that you have to solve for, and x to the I is the basis function set. So fx is considered unique and interpolary if d plus 1 is the same as the number of points you need to fit. And so all we're doing in Moose is we need to solve a linear system. Or what we're doing in this case is solve a linear system to find the coefficients. In Moose's case, your basis function set is, we have a set of points, 1, 4, 3, 1, and 4, 2. Substitute that data into a linear system, and then we can solve for a, b, and c. And so we have these coefficients, and then now we have our final solution function. So the important thing to note here is the solution is the function, not the coefficients themselves. The coefficients were given, but of course we wanted it to be defined anywhere in between, so it's an interpolation. So we can evaluate it at a particular point in space. So finite elements is you're numerically approximating a solution to PDEs. So we're doing what we just did, but we're doing it with a here. So the Galerkin finite element method is specific in that it's different from difference in finite volume because it finds a piecewise continuous function that's an approximate solution. So you are adding up these shape functions, evaluating the point, multiplying by your coefficients, and then it has a much longer mathematical history. So like we were talking about earlier, the idea of a weak form or a variational statement or a weighted residual, you'll find it in the literature under all these names. So the weak form, like I said before, the weak form involves writing down the paper form of the PDE method. Your test function is the same as your basis function that you're using to interpolate. Then you're integrating the whole equation over your domain, and then integrating by parts to get out your boundary condition terms and your kernel terms, to use Moose language. So again, the benefit of it's when you're interpolating, it's valued over the whole domain, but you're trying to localize it to be valid in each individual mesh location or cell location. So let's see. Again, this is similar to what we were saying before. For example, with the diffusion style equation. Again, we are integrating, we're multiplying by Weierstrass function, integrating, and then separating it out to find the terms that are relevant to us. So we've already gone through this example a couple times, so I'm gonna go ahead and skip through that. But then again, we have our strong form of our diffusion, and then an advection term. So we arrange to get 0, we multiply through by our test function, we integrate, and we apply our divergence theorem. So after we get this, we have our kernels, our boundary conditions. I didn't realize I put quite this much about this in these slides. So a kernel is Moose for a piece of physics. So your diffusion in your equation will be a kernel, or your advection term will be a kernel, or your reaction, like say there's a reaction term, that'll also be a kernel. So anything that's
boundary conditions are the sidebars.
okay.
So sometimes people say like I have a material kernel, but they actually mean material class. So kernel really means the volumetric kernel.
Yeah, that's a good clarification.
So like the second term that he has there in the equation, that's not a kernel. That would be a boundary condition.
So
Different type of an object.
right. So as David was saying, so a kernel is a volumetric term in this equation. So a lot of people get it wrong when they're asking questions about it. Okay. So does anybody have any questions about any of that before I move on? So we're about to get into talking about shape functions that we're interpolating against, as opposed to the general method. Okay. So for our, so the weak form is what you need to add physics. But then in software, the work is a little bit, is a 2D form of the linear Lagrange basis function that I was talking about earlier. So it's 0 at the points around it and 1 at the point that you're interested in, and then linear in between. And so they're also called hat functions because of their shape. But we need to get our equation in a form that we can make U. And so U is our solution, UH, is made up of a sum of UJ, our coefficients, and phi j, our basis functions. So the gradient can be expanded in a similar way. If we expand this out, our coefficients, because they are constant, they pull out of the gradient. So we have so like I mentioned, in the Galerkin finite element method, the same basis functions are used for both the trial functions and the test functions. The trial functions that make up your interpolation, and the test functions that you multiply your strong form by in order to get a residual form. So substituting all of this back into the weak form that we generated earlier, then we have our Moose code. Okay. So typical families for this, and those that you'll find in Moose, are Lagrange, Hermite, hierarchic monomial, and I'm not sure how to pronounce this word. Clos-Touche. Please correct me if I'm wrong. So Moose has support for all of these. Most of the time when you're getting started, directly respond to the value of the functions of the nodes, which is why we're using them as the default. And they're the easiest to understand. So this is just a visual example of all of these in terms of order. So you have linear Lagrange, you have a quadratic Lagrange, the second order, third order, and then fourth order, or cubic Hermite, sorry. So these all of what your needs are. So if you have a wildly oscillatory problem, you might want to use a higher order basis function in order to be able to capture all of that. Okay. So in terms of 2D, here's an example of a 2D Lagrange shape function. So when we're again, if we're on a corner node on the other edges, and then if it's associated with the center, it's going to be 1 in the center and 0 on the edges. Okay. So before I move on, does anybody have any questions about that section?
So can you elaborate on how do we decide which basis function?
Well, that's pretty problem specific. So if you run, in practice, like if I were to start a problem, and I ran it with a linear shape function, and I was getting either results that then I might try upping the order to see if that's helpful. And for certain applications, you sometimes the higher the order, the better. Sometimes not. So it's just entirely dependent on the specific type of problem that you're trying to solve. So that was a good question. Thank you. Anything else?
So start low and then go high if you need to.
Well, yeah. I mean, so the default's first order. So for electromagnetics, say you're using sometimes you're using vector basis functions, and first order might not be enough, depending on what sorts of geometrical concerns you might have and that sort of thing. So my rule of thumb, my personal rule of thumb, David might have a different idea, but I generally tend to start low and then go high if I need to. Numerical integration. Now, this is the only part that we haven't discretized yet. So we're splitting the domain integral into a sum of integrals over each element, so each cell in our mesh. So most of you probably have an idea of what we're doing here. So we're mapping our between the physical domain to the reference element that we have. And so this Jacobian is important in Moose code as well as just important in general. So we're approximating these integrals numerically using quadrature. And so the quadrature is the xq here is the spatial location of the qth quadrature point, and the weight that is associated with that quadrature, and that's determined by your quadrature rule. That f of xq part of that term. So under certain situations, this is exact, right? So if you're in one dimension, then the Gaussian quadrature can exactly integrate polynomials of order 2n minus 1 with n might be important based on what you want your numerical integration to be. So then, since we're sampling at our quadrature points, the u that we had earlier and is our sum over uj phi j at these quadrature points, equation we had earlier, but mapped with our Jacobian and our quadrature rule. And so then this is our term over the faces of our cells. So Moose needs to provide the quadrature points for where you're interior of the cell or on the face as necessary, and it determines that. Okay. So some I 1 through n equaling 0, so we want to solve for those coefficients. And so we use it to solve on the nonlinear step, and we're finding the roots of this equation. So for a scalar equation f of x, so getting from x, so we're updating by going from our my mind just blanked. Sorry. So anyway, I'm going to move on. So we don't have one scalar equation here. That's the important thing to remember. We have quite a few. So this leads to this form where the Jacobian comes back in again. The Jacobian matrix evaluated at our current. It's important to note that, oh gosh, it's not my forte. Let's, okay. Okay. So after for Newton, for a simple problem our sample problem as before, we have our residual. So the ith component for residual of our solution over each individual coefficient, and our derivative of our gradient over each individual coefficient. We can get the Jacobian for this, and for a simple equation, you might have a non-trivial Jacobian. So simple thing, you're taking the derivative of that, and so your Jacobian statement would simply be your coefficient times your basis function. But if you have a coupled term, then you're going to have to consider the Jacobian contribution for each individual coupled term. So like I said, they depend on the partial derivatives of all of these, which could be difficult or time-consuming to compute analytically. So the method is we don't need to calculate this Jacobian, though you can turn on full Newton and use the Jacobians that you calculated. Or you can precondition by using your Jacobian statements and developing a finite differencing your residual statements in order to calculate a Jacobian internally to Moose, and that you can use that to solve your problem as well, or to precondition. Yes.
There is also a damped version of the Newton method.
Yes.
Is that important?
So there is a dampers class in Moose, and I'm not quite as familiar with that. Is David in the room? David, do you know much about the dampers system, the Newton dampers in Moose? Could you come up here and get a microphone just so it comes through on the audio?
Yes, there is a whole system where you can actually dial up how much you want to damp on different quantities. So let's say that you want to damp with a constant. So we give you a constant damper where you just say, I want to damp by, let's say, 10%. It'll do it. But let's say that you want to run some kind of computation on your mesh, and you want to figure out, like, okay, so let's say that I integrate. Okay, good, thanks.
Does anybody have any? Sure.
For the Newton method, we need a root to predict the initial root.
Mm.
And then if your prediction is close to the true root, then the Newton method very good. But if your prediction is
So I'm not as familiar with the nuts and bolts of that. Can you step in, David? Turn on the microphone, by the way. I don't think it's on.
No, I think it's turned off. There must be a button.
There's a button on the side.
Let me check.
Sorry.
Test? Oh, okay. So the Newton solver is a line search, and so that might help you to get you to the root the way you want. But of course, like, your initial guess is is what ultimately decides, right? So when Casey was showing the steady state simulation first, and when he talked about the initial condition, that was actually your initial guess for your Newton solve. When we get to transient, your initial guess is going to be the solution from the previous time step, and that'll be used as an initial guess for your Newton solve.
Okay. So the Jacobian-free Newton-Krylov method is the so we have our system of AX equals B, where A is our Jacobian, X is our delta UN plus 1 from the Newton method, and B is our negative residual, and so main fixed. So the linear residual is defined as a rho equals the Jacobian multiplied by the iterate minus our residual. And so Moose prints this for every linear step, which is what you saw on the screen during step 1. And so if you set print linear residuals equals 2, true, it'll show you that, but that's on by default. Okay. And so I'm not as familiar with this portion, so I'm leaving this as a reference. But the Jacobian-free method, or Jacobian-free Newton-Krylov method, has a lot of different settings, different versions of it, and I'm gonna leave that for because this is okay. So essentially what we're doing is we're approximating the Jacobian. So saying the residuals are multiplied by our, let's see. So we're getting, Moose is determining this approximation, but we don't have to do any analytic derivatives to determine the Jacobian. We just need to, the time we have to take is just for the residual computations. If we don't want to take up that much room in memory, then the Jacobian-free Newton-Krylov method is a good way to do it. Okay, so to sum up, so we're using the finite element method as a solution to our PDEs. So we're finding the coefficients for our basis function, and the solution is the combination of all these coefficients. In Moose, they compute integrals numerically using the quadrature, and then we're using Newton's method to do the nonlinear solve, and the Jacobian-free Newton-Krylov method allows us to Jacobian while still computing the solution as if we had the Jacobian. Okay, so after all of that, does anybody have any questions or concerns? Yes. Yeah, I think it's probably time for a coffee break. I'm definitely in need of one. So we'll take about 30 minutes, and we'll be back in around 10:50, 10. So I was given all of that mathematics content by the Moose team, and I was.
Jannis, Jannis. I'm guessing you're from China.
Yeah. Apparently, I see a lot of people, at least I know, same name.
I've seen it too.
I'm not sure how. So what are the loading step? For the packages themselves, there's one newly installed. Or 0%. So I think everything else is pretty much up to date.
Once that's done, you need,
I would say right now, if you haven't already, download the environment. Oh yeah, it's downloaded. Okay. We'll try downloading the environment. If there's any errors of this, then yeah, that means we'll have to go and upgrade your because that's unfortunately that's not this problem. Yeah, that's an Ubuntu problem. I have to go on this tab. So yeah, we'll do this. Download this. This is a big problem. I think we'll go to later on. Or recommend but right now, like it's built from this particular tutorial. have the tutorial app. It's running. Do you have Paraview or I have Paraview. Check it so you're all set. Let me know if you have any more questions.
Yeah, so basically I have deployed it to 5.1.
Okay, yes. So, reading materials, I don't know too much. From the basics, what I recommend is there's a free course that Michigan offers. It's on YouTube. They provide some learning materials. Yep, second one right here. They have. So here's the playlist. They have 160. They go through them all the way from scalars, operators, and then vector operators. This is done by the mechanical department. So their example is stresses on. Yeah, it stresses on a beam. Yeah.
Something that deals with fluid stuff. So
Yeah.
then the thing is that if you
Almost all of it is either was a pure math class or a subsection of mechanics. So I think I saw one of those in space. I don't know who was delivering that one.
All right, so try to run a case in Peacock.
But anyway, he tries to make the videos as general as possible. So it talks about taking the strong form, which is a regular set of equations, multiplying by a test function, or iterating over a test domain, turning it together pure residual, and do a combination of
Yeah, so
non linear methods.
It already did it. If it's actually building, it should be
Some
out.
values is comfortable with. But yeah, this is great speeding research. Okay, yeah, no problem.
So this is giving you, okay. So we go back to our command line. And so instead of saying, or your other terminal, so what you would say here is you would say, okay, so it's found your executable. Let's exit back out of it so we can get back to just a terminal prompt. So let's exit out of Peacock altogether, go up to the window and just quit. Yeah, quit. So now we're here. You would type Peacock like you did here, but in order to look at a specific input file, you would put in space, and then the actual input file that you want to look at in Peacock.
input file.
Yeah, the input file that you want to look at visually. So it would be easier. Let's changes you make here will get save it. Save it as a text editor file. Yeah. So instead so it's everything's organized in blocks. And you can read those blocks as doing a periodic boundary condition, but it's not selected, it's not turned on. But if you click on this, it'll show you. I'm not very familiar with using Peacock. I don't tend to use it.
I think that was the issue was, I don't know, maybe go back to your account location and see if it's maybe
So double click, it'll show you the name that was given us, the type part, the boundary over time. Now Peacock is giving you the option of editing it, and the options that you may have. In this case, I just have the option of then you can put in comments, and even these comments you have to write on it as a file. So it'll do quite a bit. There are some things, like certain visualization, and there are certain blocks that Peacock, that are new, that Peacock I would be doing this type, this, this gives you all of it. And you can turn things on, turn things off.
So maybe you should just
You know, and it gives you context.
If I send it here, I save it.
It saves it to that in a text info file. So you can distribute that, and you make your changes, and you can open it back up. If you're not going to more changes, or you can edit it in a text editor. With your simulations outputting, running it, and adjusting the files and stuff like that.
Oh, so maybe
That's
kill it.
this is a very, very powerful piece of software if you are
Probably
getting started. Once you kind of have your feet wet, you may not even need to use this anymore. You may just be writing text input files. But when you're getting started, especially, it's going to see all the options available to you.
But it does have limitations.
A lot of things run. And then it would show you the what you would see.
that's why you have extra
Now, double click on the
folder probably block out.
Okay, it might just be, might just be a short Peacock on my computer. Yeah, if you go to
Hopefully that'll know that maybe it's because so many people are downloading it. Yeah? Yeah, so would you... Yeah, instead of, this is...
Yeah, so actually Peacock uses PeerView, it has bits and pieces of PeerView to display your data, but not all.
You didn't.
So that's why it looks nice.
The
You
update.
go into Peacock.
Oh, look, I'm getting some progress.
So it uses bits of PeerView in order to display the stuff.
I can find.
PeerView is pretty flexible. So, but again, Peacock is very much in development. It has to limit every time there's a change to MoveSet, you have to update Peacock to fix some issues. So as you use it, if you decide you want to use this